A trough is 10 feet long and its ends have the shape of isosceles triangles that are 3 feet across at the top and have a height of 1 foot. Let's stop right there and draw a picture. All right, so we've got isosceles triangles 3 feet wide at the top, 1 foot tall, and then the trough is 10 feet long. Now the trough is being filled with water and we want to know how fast the water level is rising. Notice because the trough is narrower at the bottom, at the beginning, it's going to be rising faster than when it's like halfway full. It's going to start to slow down, like the depth of the water is going to slow down because it has more volume to fill before it can actually increase in height. Well, let's go ahead and visualize some water here in the trough. There we go. And water is coming in. Water is coming in at a rate of 12 cubic feet per minute. Folks, think about what happens as water comes in. The volume of water increases. This is a volume, cubic feet. So we want, we are given that dV dt is equal to 12 cubic feet per minute, right? We have water coming in. As water comes in, the water level rises. That is going to be a dH dt, and that's what we're after. How fast is the water level rising? So that's what we want. We want dH dt when the water level is 6 inches deep. Let's note right now, 1 foot here, 3 feet here, 12 cubic feet here, this 6 inches. We're going to say we want dH dt when the height is equal to half a foot. And I guess I'm doing this in blue. What's the volume of the trough? And I don't actually care about the volume of the whole trough. A lot of times people will write that number down. That number doesn't do anything for us. What I need is a variable volume of the water in the trough. And, but it is the shape of the trough. Now, if we had a cylinder, we would say that the volume is pi r squared, say L, where L is the length of the cylinder and R is the radius of one of the ends. It's based on the area of a circle times a length. If we were dealing with a rectangular solid, let's say the rectangular solid, oh, that looks terrible, much better. If this had a width and a height and a length, then the volume of the rectangular solid would be, I'm going to write it as width times height times length. And the idea here is it's the area of the rectangle on the base times the length. So in both of these cases, we have the area of a face times the length. The area of a face times the length. And so for our trough, we need the area of a face, which is now a triangle. So this is going to be the area of a triangle times the length, which is 10. Let's get rid of these things now. Now I need this area of this triangle. And again, I'm not going to use a 3 and a 1 because that's the area of the whole face of the trough. I'm also not going to use a 1/2 because as you've noticed, I'm going to plug in a 1/2 after I've taken a derivative, right? I want it in terms of variables until I differentiate. Otherwise, everything's a constant. Derivatives are all 0. So what we're going to do is let's examine the triangle on this side here. It's an isosceles triangle. So here we go. Actually, you know what? It's 3 feet wide at the top and 1 foot high. I know I said we aren't going to use it. We aren't going to use that in the formula, but we need it now. And then we've got some, say, water here. Folks, that water will make a whole other isosceles triangle. The height of that water, I don't know, h. As for the width across the top, I don't know, call it x. Now I have these similar triangles. You see, 1 is to 3 as h is to x. Another way to put that is that h is equal to 1/3 x. All right, that's cool, but what does that gain us? Now I have a connection between x and h. So what? Well, remember that the area of a triangle is 1/2 base times height. And so in this case, the area of our blue triangle is going to be 1/2 x times h, right? Base times height. And I just realized I don't want this to be h is equal to 1/3 x. I'm kind of glad that happened though, because it gives me a chance to talk about it. I want dH dt, which means I want the volume of my trough to contain an h in it, right? Ultimately, what I'm going to do with the volume is differentiate it so that I can use the dV dt. And then if my expression includes an h, then I'll end up using, or I'll have a dH dt, and that's great. In order for me to keep an h here, I want to substitute out the x in a equals 1/2 xh. If I'm going to substitute out the x, then I need to isolate x, which means that I actually want to say that x is equal to 3h. All right, so the area of the blue triangle is equal to 1/2 x, which is 3h, times h, or 3/2 h squared. That's the area of the triangle. That's the area of the face of water, if you will. The volume is going to incorporate length. And so the volume of the trough is equal to 10 times 3/2. That's going to be 15h squared. At this point, we can say then that dV dt is equal to 30h times dH dt. Now let's look back at what we have and what we need. What we want is dH dt. So I'm going to solve for dH dt when h is equal to 1/2 and we have that dV dt is equal to 12. Therefore, you can check the math on this. dH dt is going to be 12 over 15. And divide out the 3's. We end up with 4 over 5, so 8/10 of a foot per second. Tidy that up with a nice sentence, and there you are. And in case you're not sure what 8/10 look like, it looks like it's about 9.6 inches per second, but we weren't asked for that.